we're going to go through what's called trends. Okay? What is a trend? What's that, Adam?
Something that keeps happening.
Something that keeps happening over and over again that you know is pretty consistent. It's going to happen.
Kind of like a fashion trend.
Fashion trends come up. They change over and over. So when you guys see yourself in the yearbook 10 years from now, and you look at the clothes that you're wearing, some of you are going to be going, man, times have changed. All right? I look back at my yearbook, which I don't ever really like to do at this point in time. But you see some things changing, trends changing. And a lot of times they come up again. Okay, those trends will come up again. The trends we're going to talk about have to do with a value either increasing or decreasing. Okay? So it's either going to be increases or get smaller, decreases. That's all you're going to have to remember. But you're going to also have to apply the trends. You've got to memorize the trends. As if we go across the period, what happens to, for example, the size of that atom. If you know that trend, then you could go ahead and compare two atoms on the periodic table and tell me which one's going to be smaller or which one's going to be larger. You go down a group and you know the trend, and what happens down a group, you'll be able to tell me and compare two atoms and tell me which one is smaller or which one's bigger in that trend. Okay? So after today, you'll understand more about that. It's just not going to be some just general information I just gave you. It's going to be more specific. So if you want to read through those pages, you can. You're more than welcome to. There are 5 trends. There are only 4 on this page, and the 5th one I'll give you tomorrow. I'll give you an additional page that will run off. Right. The first trend is probably the easiest trend, and it's the easiest to understand that we're going to have, and it's atomic radii. I'm going to give the definition. You can write the definition down that's in the book. It'll be real similar to the definition that I'm going to give you. And then what you can look is on page 151 at figure 13. And we do not look at D's. We're not going to look at any D, the middle group. We only look at S's and P's and how they compare. That's all we're going to look at. So don't look at any D, size, numbers, or anything associated with that group, or the F's, which we definitely didn't do last unit when we were going through those. Okay, so I'm going to go ahead and give the definition that's similar to the book. You can write that one down, or you can write this one down. They're just worded maybe a little different. This is atomic radii. So we know the radius is from the center of a circle to the outer portion, right? Okay. So how do they measure this? They take 2 atoms. They're looking at 2 atoms. They're bonded together. And they look at the distance between the 2 nuclei of those 2 atoms, and then they measure that distance, and they take half that distance. And that is how they come up with the size of the atom. So basically, atomic radii is just this relative size of atoms. Okay. So as we go down through this, we've got this thing called period trend. Okay. Period trend. So as you go across a period, and all of these are going left to right. Like you would read left to right. Everything we talk about with trends and periods is left to right. We could go right to left, and that would be okay, but everything is going to be left to right. So what is the trend, as you look on page 151, for the period trend? So I'm going to have somebody volunteer or call on them. We just look at either the numbers that they give us, that gives us the radii, and the circles are relative sizes of atoms based upon that number that you have there. So anybody have an answer for the trend? Does it get bigger or smaller going across? Raise your hand if you got an answer. Yes. Oh, I thought you were raising your hand. Okay.
Smaller.
Okay, smaller. And what did you look at to get that information?
The italicized lettering.
The what?
The italicized lettering. It looks like the definition.
The numbers?
Yeah.
So, like the second row, 2 through 10, goes 152, 112, 85, 77, 75, 73, 72, 71. So there's a consistent decrease in the radii. You can also look at the circles, and they're getting smaller. They're a little bit tougher at the end to differentiate between those sizes. That's why you use the numbers. So the atomic radii gets smaller, right, across the period.
Well, yeah.
In general, it's not going to be perfect all the time. These trends are not 100%. There's always going to be some situations where that may not be the case. We don't want to look at the D's. Remember, we do not look at the D's. We cross that section out. We don't care about the D's. We're only cared about the main group elements. The main group elements are S's and P's. Those are the ones we're concerned with. So the period trend is to get larger. The radii gets larger. Or I'm sorry, the radii gets smaller. We're going to come back to the reason. So now we're going to look at the group trend. You guys could probably get the group trend and look at the groups. You guys go ahead and write out what the group trend is. I don't think I need to tell you. I will here in a second. But go ahead and predict what the group trend is and write it down. So groups mean going down a column and looking at the size of the atom. Anybody got an answer for the group trend? Adam?
It gets smaller.
Gets
No, it gets bigger. Sorry. It gets bigger.
Gets bigger. Okay? So the group trend, we're not looking at the reason yet, but the group trend radii gets larger. This first one is listed at the beginning because a lot of the other trends depend upon size of the atom and where the electrons are located. So when we talk about this unit, we're really focusing upon electrons and where they're located. Right? So the size of the atom is dependent upon electron cloud. If the electron cloud gets further away, then the atom's bigger. The electron gets closer to the nucleus, and the atom gets smaller. So it's electrons. So what keeps the electrons in place? What keeps them from flying off? Brendan, what keeps electrons from leaving?
Is there a magnetic field?
Kind of like a magnetic field. You probably won't want to say magnetic field, but what keeps them, Eli?
Nucleus.
The nucleus. What's in the nucleus? Brittany, what's in the nucleus?
Gravity?
No, it's not gravity. It kind of acts like gravity, but it's not gravity. You should know.
Protons and neutrons.
So which one of those two keep the electrons in check? Keeps them where they're at.
No,
Neutrons are neutral charge.
Oh, then protons.
So protons are positive charge, and they keep the electrons there. analogy would be, as you start off as a baby, do you think you need a lot of care? Do you think a lot of resources, a lot of time is spent with babies, right? Parents and their kids, right? Then there's less and less involvement parents have with their kids as they grow up. Sometimes that changes, but for the most part, as you grow, you get more and more independent. Right? You don't have to depend upon your parents to tie your shoes, right? Okay, or other things that you should be self-sufficient at, right? They shouldn't be having to tell you, do you know you got an assignment that's out? Can you get that done? Can you get that made up? It's missing, it's a 0 now. Are they still doing that? They shouldn't be still doing that. They shouldn't be still going, all right, how come you don't have this assignment in? Are you going to retake that test? If you got a bad grade on it, you might want to retake it. So you become more independent. Now when you get off to college or go off to work and get away from home, they have less and less significance with that, you know. As parents, we struggle with when our kids leave home. It is not an easy thing, transition. It's easier I think over time it's easier for example, my kid, Rebecca, I think it's easier for her, and she's making that transition, making friends, and experience life in a different way. It's tougher on the parents because the parents are losing somebody that they're always, you know, have been with and enjoy some of the accomplishments they're doing and going through. But these electrons, if they get further and further away from the source of the nucleus, they're easier to take away, to take out of the atom. If they get closer and closer to the nucleus, it's harder for them to leave because there's a stronger attraction between those. So that's going to be our trends, all right? So any questions on the trends? Gets smaller going across, gets larger going down. Now, atomic radii is going to be significant because that's the only trend where it gets smaller going across and gets larger going down. The rest of the trends we look at are going to get larger going across and smaller going down. Though we haven't got to them yet, that's going to be the case. All right? So let's go back to period trend. The reason that we have that trend, there has to be a reason for each one of these. We just can't say, well, here's the trend, let's go on. We don't care about the reason. There has to be a reason for each trend that we see. So why does the radii get smaller? So what do we know what's happening to the atom? How's it changing as it's going across? Mr. Buss, what's changing in it? As we go from element 3 to element 10, what's changing? Yep, number of protons are increasing by 1 each time in the nucleus. So what's happening? The charge of the nucleus is getting bigger and bigger and bigger. Okay? So what else is happening? Okay, what else is happening to the atom? So you're adding protons. What else is taking place?
The electrons are getting closer.
They are getting closer, and because you're adding more and more electrons. So you're adding additional electrons to the same shell, right? Okay, you got 2s1, 2s2, 2p1 through 2p6 are added to the same shell or same region. Okay, that's what's taking place. Adam.
So like the nucleus is getting bigger than like the.
Well, it's getting stronger in charge because the nucleus is really tiny. It's the main thing. Its charge is getting bigger.
So it's not like physically getting.
Well, it is a little bit, but it's so far from the electrons relative to the electrons that it's more about the charge than the size. Okay? Yes, Nathan?
What are the units that the atomic radius is measured in?
Picometers. Picometers is to the minus 12. So it's smaller than a nanometer. So those values that you don't have to know that, but those picometers are measured to the minus 12. So if we would go a little bit further than nano, we'd go another 1,000 smaller than a nano, and that's a pico. Okay, so that just tells you how small these atoms are going to be. Right? So you know what's happening going across, right? It's adding more protons. to the nucleus. It's adding more electrons to the same shell. So does anybody have an idea why that electron cloud starts to close in and get smaller and smaller and smaller? Jared?
Trying to keep the electrons?
Yeah, well, they're all trying to keep the electrons, but why is it sucking it in? Yes?
Is it stronger pull?
Yep, there's a stronger pull because more protons are added to the nucleus, which create a stronger attraction for those electrons in that shell. Okay? Those electrons want to repel one another, but the protons kind of take over, and it's called a nuclear effect. So we have a greater nuclear effect on those electrons. I tried to make that as short as I could. The idea called the nuclear effect. What's the nuclear effect? Nuclear effect is you're adding additional protons to the nucleus, which will cause, the effect would be that there is a greater pull on those electrons in that same shell. It's like magnets getting stronger that are placed next to one another. There's just a stronger attraction. Kind of like gravity.
Well, it's the sun.
Kind of like gravity.
The sun's like barely getting the gravity's getting stronger.
Yeah. The farther you get away from the sun, the less gravitational pull it has on things. Yeah.
So it's like
Yeah.
the sun's
The farther we get away from the center of the earth, the less gravitational pull is there. But this here, as you get closer, supposedly this is what happens. I don't know if it works. You'd have to have a real sensitive scale. But if you weighed yourself in Death Valley on a scale, you have a weight there. And then you go to Mount Everest, at the top of Mount Everest, and you weigh yourself there. Okay, and you haven't lost any weight. You're the same weight. You would weigh more at Death Valley than you would at Mount Everest. The reason? Because you're closer to the center of the earth. When you're closer to the center of the earth, there's more pull. If you're farther away, there's less pull. There's less attraction. Okay? But the reason for that is because you're adding more protons to the nucleus, which in effect has a greater pull on those electrons in that same shell. The key is the same shell. Because we could go down a group, and we're adding more protons as we go down a group, but we have bigger atoms. You say, well, we're adding more protons, but we have different shells that are introduced as you go down a group. So the group trend's easier, guys. The group trend is less wordy, more easier to reason. So the group trend for reason that we'd have, anybody have the reason for why they get bigger?
protons and
Well, let's try not to use protons. What is the key word that we use that we know what's happening as we go down a group?
Increase.
They increase in size, but why?
get closer.
What do we know about electron configuration as we go down a group? It goes from, like, for lithium would be 2s1. So what is sodium?
It goes in like runner shells.
You add an additional shell each time down a group, right? Then it goes 3s1, and it goes 4s1, and 5s1. We are adding shells on. Okay, the reason is additional shells added. down a group. That makes sense? Why? Well, we're adding on an extra shell, extra energy level. Any questions you have with that? I probably took a little bit more time on that, but that is an important concept, important idea to know what happens to size. So, for example, how do you apply this? So if I ask you, well, which atom is bigger, magnesium or silicon? You will say what?
Magnesium.
Magnesium. Why?
Down on
Because
the
it has more subshells. It has more shells.
Nope.
It's got more protein.
What's that?
It's lower and it's farther to the left.
Yeah, yeah. So the trend is to get smaller going across. So magnesium is before silicon. Am I in the right row? Yeah. So that's the reason. The reason is because as you go to the right, the atoms get smaller. Correct? So you just have to apply the rule. Okay? We always want to apply the rule, and that gets us to know it a little bit better. All right, next one. You guys need to turn over to page 153. 153. The ionization energy. It's the energy required to take out the first electron take an electron away from a neutral atom. So we're going to take an electron out. And so there's some different energies associated with this. These are energies that are not just the first electron, but the first mole of electrons. And so the unit used for first ionization energy is joules per mole of electrons. So we're going to take out not just one electron, but a mole of electrons, which would be 6.02 times 10 to the 23rd. So these are going to be measured in joules. Okay? Measurement in joules. They're going to be the first ionization energy. Now, I take that back. Kilojoules. It is joules as a base unit, but it'd be kilojoules per mole. All right. What I want you to do on your own, look at the S's and P's, and I'd like you to put your trend in for the group and for the period. Period being first. Look at that trend. Look at the numbers, and the numbers will tell you what the trend is for the S's and P's. So go ahead and look at those two trends.
Can you go back?
So what is the period trend? Bigger or smaller? Okay, it gets bigger going across. Ionization energy increases going across. Okay? So going down,
Smaller.
smaller. So the group trend going down is ionization energy decreases.
Wait.
Okay? Adam, we are on page
No.
153.
I'm on that page.
Okay? And then you got to look at the trend. Okay? So as you go across the period, the values get smaller. Or, I'm sorry, the values get bigger. Right?
Right.
So that means ionization energy increases going across.
So are there like atomic radii and ionization energy kind of like wavelength and frequency kind of?
They're opposites,
Yeah.
but we
like
they
that.
one will depend upon the other, and so we'll get into the reason here in a second. We'll get into the reason because the size of the atom has a huge role in why it's tougher to take out electrons going across versus going down, why it's easier. Because going down, it gets easier to take out electrons. It's easier to take those electrons away from the atom as you go down. So ionization energy decreases going down. So can anybody tell me why you think ionization energy increases going across? Why it becomes more difficult to take an electron out of an atom?
There's a higher charge.
Right. There's a greater pull on those electrons because of the nuclear effect. Right? That would be the main reason, and because of that, the electron gets closer to the nucleus. So what do you know about attraction of electrons that are close to the nucleus versus ones that are farther away? Greater pull. And so it's like a tug of war. You're going to have to pull that electron away from a source that's pulling it in with a strong force, and it's going to be more difficult to pull it out. So it's going to take more energy to pull that electron away. Okay, so I'm going to give the reasoning for the period trend. It all has to do with the atom getting smaller. Because of that, there's going to be a greater attraction between that nucleus and that outer electron. Getting closer to a source that's pulling it in. It's like the example I gave you with gravity. Closer to the center of the earth, you're going to weigh more. There's going to be a stronger force there. If you're farther away from the source, it's pulling you inward, there's less attraction. Easier, less force to kind of pull against. Okay. And the group trend is going to be opposite of that. You're farther away from the nucleus, which means less attraction for those electrons by the nucleus. There is another thing I said I wouldn't tell the other group, and you don't have to put on a test. It's called a shielding effect. And the shielding effect is you get farther and farther away from the source. It's kind of like a playground. And you got these kids, and they're playing around on the playground. And they're all kind of centered. But then you have these individuals that get further and further away from that bunch of kids. It's probably maybe easier for that kid to get attention on him. Becomes less for those who are watching during recess. And that you hear about every once in a while that somebody disappears because there's no really focus on that person that's outside of all those kids in the middle. So it's kind of like that idea, shielding effect, there's more and more electrons between the nucleus and those outer electrons, so it's easier to take out that electron because of that fact. You won't have to do that, that's just an additional information. But the group trend, the reason for it is atomic radii gets larger. Okay, what I need you to do, you guys have got 5 minutes. What I need you to do is when you turn over and look at ionic radii, I want you to write a page number down. And that page number down that you're going to look at for ionization or ionic radii is page 159. Page 159. When you turn your page over, it says ionic radii. And I would want you to answer all those questions as best you can under ionic radii on your own. And then we'll talk about it tomorrow. That's your assignment. Your assignment is to define ionic, don't define ionic radii, but define cation and anion, and then answer those questions down below. Okay, so page 159, in your guided notes, you have ionic radii, you have cation and anion, and then you have questions listed down below. Answer those questions for tomorrow. How you read the chart, I want you to look on page 159. The red circle represents the atom that has gained or lost an electron. And you'll know if it gained or lost an electron by its charge. If it's a positive, it's lost an electron. If it's a negative, it's gained an electron or 2 or 3. The green circle is the first initial circles we looked at when we looked at atomic radii and their trends. So the green circle represents the atom that's neutral. The red circle represents the atom that's charged. So there's no really trends we're looking at here. We're looking at more of areas on the periodic table and what's happening in areas. And we're less looking at trends. We're not going to look at a trend as in across a period or down a group. Okay?